Today we're going to look at section 3.2a, solving systems by substitution and elimination. So our objectives are to solve using the substitution method and to use the elimination method, or sometimes also called linear combinations. So what is the substitution method? And you don't have to write this down word for word, but just kind of paraphrase it just for your own notes so you understand. It's when we solve one of the equations, and you can choose whichever one you want, for one of the variables, and usually it's x or y, and again you can choose. And then what we do is we take that, whatever its value is, and substitute it into the other equation. And that way it gives us an equation with one variable, which we're able to solve. Elimination, or linear combinations, is just how it sounds. Our goal is to eliminate all of the variables except for one in order to solve again to have an equation with one variable. And what we're going to use is a combination of multiplication and addition to make this elimination possible. So let's first look at an example with substitution. So what we want to do, if we remember what it says, is we want to get one of the variables, in this case x or y, by itself. If we look at the first equation, y is already isolated. So it's nice and easy. We know that y is equal to this value. So wherever I see y in the second equation, I can substitute that in. So that's what I'm going to do. I'm going to take 3x plus, instead of y, I'm going to substitute. I'm going to use parentheses. It's always best to use parentheses when you substitute, just in case you have to do a special operation to it. But because there's only an imaginary one here, I don't really need it. So I can look at this as if the parentheses didn't exist. So I have 5x plus 8 equals negative 2. I'm going to subtract 2 from both sides. Subtract 8 from both sides and get negative 10. Divide by 5, and I get negative 2. Now, I don't stop here because when I solve a system, if you remember from our last video, solving a system means we're looking for points of intersection. Well, this is not a point right now. It's half of a point. So I know that part of my solution is negative 2 comma some value for y. Well, how do I find y? I'm going to substitute this in. The best place to substitute it in is for my first equation, because y is already isolated. So 2 times negative 2 plus 8, negative 4 plus 8, gives me a value of y is equal to 4. And this would be a nice solution. Now, you should double check. If it's a solution for a system, if you remember, it should make both statements true by substituting in. Let's look at this, another example. Now this one's a little bit tougher because the x and the y, neither of them are alone. But if I look, the first equation, to get x by itself or y, I'm going to take a little bit of work. If I look in the second equation, if I just subtract both sides, subtract the 2y from both sides, I can get x by itself pretty easily. So now I can take this, and anywhere I see an x in the first equation, I'm going to substitute in. And this is a place where you definitely need to use parentheses. So we get 5 times the quantity of 3 minus 2y now. Minus 3y equals a positive 2. I'm going to distribute it at 15 minus 10y minus 3y equals 2. 15 minus 13y equals 2. Subtract 15 from both sides. I'm going to get negative 13y is equal to negative 13. And then finally divide by negative 13 gives me a positive 1. Again, remember this is only half of my solution for my order pair. I'm going to go back, and since I know what x is equal to, I'm going to use this equation and just substitute in a positive 1 wherever I see y. So I'm going to get x equals 1. So again, I get a solution of 1, 1, which means if I substitute 1, 1 into both of these, I'm going to get 2 true statements. So let's look at an example with elimination. Now, elimination, I don't have to get x or y by itself, but the important key is to make sure everything lines up. I want to make sure my x's are above and below each other, our y's, my equal signs, and any constant on my path. So now I'm going to look and think, if I add these equations together, will anything eliminate? So 3 plus a negative 2, well, that doesn't go away. Negative 6 and a 1 doesn't go away. And I don't care about the numbers, but remember we want to eliminate a variable. If something doesn't eliminate, our goal is to make it eliminate, okay, by doing some sort of multiplication. Well, I'm going to choose to eliminate the y's in this case. And I know I can do that. If I multiply the left side and the right side by 6, I'm going to get a new equation. I'm going to get negative 12x plus 6y equals negative 18. And if I rewrite the top equation right above it, I'm going to see that I have my y's are both a value of 6. One is positive, one is negative, which means that when I add them, they will reduce to 0. therefore eliminating. So now I'm just going to add these. So I'm going to get negative 9x equals negative 18. Divide both sides by a negative 9 gives me a positive 2. Again, it's on track to my solution. Now, when I go back, neither of these have an x or a y by themselves, so it doesn't really matter which equation I substitute this in. Do whichever one you feel like the algebra will be the easiest for you. In this example, I'm going to choose the second one. You can actually choose any of these examples or any of these equations to substitute it back in. You should get the same answer. So negative 4 plus y equals negative 3. And I'm going to add 4 to both sides to get a positive 1. So my solution would be 2, 1. Let's look at one more. Here again, if I look, I can't do what I did in the last problem where I just picked one equation and multiply it by something. So I have a negative 5 and a 7, a 3 and a negative 2. So I'm going to choose to eliminate the x's this time. And I know that a positive 3 and a negative 2, I can make both of them 6 if I wanted. I multiply the top one by a positive 2 and the bottom equation by a positive 3. And I should get 6x minus 10y. And make sure you do distribute the 2 to every part, every term, equals negative 12. In the second equation, we get negative 6x plus 21y equal to 12. Now when I add this, 6x and negative 6x eliminate to 0. So when I add these, I'm going to get negative 10 and a positive 21. Gives me a positive 11y equal. When I add this, I get 0. Some students see this and they think, oh, it's gone, and then they forget to write the equal sign and 0. You can't lose an equal sign. If you have an equation to start with, you should always have an equation. So we divide both sides by 11. 0 divided by 11, remember, is just 0. Remember, it's okay to have 0 in the numerator, just not the denominator. So now I'm going to go back and choose this. I'm going to choose the top equation. Again, it does not matter. Substitute in 0 for the y value. So I get 3x equals negative 6, x equals negative 2. And that would be my solution. Negative 2, 0. Well, sometimes you get weird answers, whether you're doing substitution or elimination. All of your variables might end up reducing out to 0. So all of your x's go away, all of your y's go away. So let's say, for example, that happens, and you get down to 0 equals 9. What you need to ask yourself is this a true or false statement? And this is a false statement. So what this is saying is the algebra is confused by what you want to do. 0 doesn't equal 9. They're trying to tell you that they cannot find a point where they intersect. Well, if you can't find a point where they intersect, that means we have parallel lines. So not even graphing the lines, you should be able to tell by the solution what kind of lines you have. So we get parallel lines. And what does that tell me about the number of solutions? Well, parallel lines don't hit, so we have no solution. And the reason we have no solution is because we get a false statement. But what if we get something where everything goes away, but we get 0 equals 0, and 9 equals 9, 10 equals 10, negative 4 equals negative 4? If we get what we call a true statement, the algebra is trying to tell us that it's true all the time. 0 is always going to be equal to 0. So what happens when two lines always have intersection points? No matter what point you pick, it'll give you a true statement. Well, those are called coincident lines. And those are just lines that basically fall right on top of each other. So how many solutions we would have here? We'd have an infinite number of solutions. Again, we get that because we get a statement that's always true.